Okay, so we were talking about the fluxes over the control surface. So as you can see here, this is examples for different inlets and outlets. So as you can see here, for example, this is an inlet. So where the velocity is inclined. So what we should do, we can just give us this angle theta here, okay? And when we do v dot n, the projection will give us minus v cosine theta. Okay. Now, if you look at this case here, if you have a control surface and the flow is tangent to it, then you don't have any mass flow rate crossing the control surface. So this is why always components of velocity parallel to the control surface will not contribute to the mass flow rate, to m dot in or m dot out, since they will just be tangent to the control surface and will not cross it. So to cross the surface, the velocity should have a component along the normal direction. Okay, so here these types of flows will not lead to a crossing velocity. So v dot n in these cases will be 0. Now in this figure, you have the example of an outlet. So also here, as you can see, v dot n will give you a positive result. All you have to do is to know the angle here in between. So v dot n in case of exit will be plus v cosine theta. Okay, so this figure shows you the different possible cases. You have inlets with inclined velocity, outlet with inclined velocity, and flows that are tangent to the control surface and that will lead to a zero flux crossing the surface. Okay, now what about moving control volumes? We have seen together until now that we considered fixed control volumes. Now, what will happen if the control volume is moving? It's not very complex. Just if you do some thinking. Okay, look, I'll give you an example to understand. If I give you a duct, okay, and you want to have flow of water inside this duct. If the duct is moving at a velocity of 2 meters per second, if I try to have water in and I just have a nozzle giving me a velocity for water of 2 meters per second, water will not be able to enter the duct. What is the condition for water to enter the duct? The velocity of water should be larger than the velocity of the duct so that I can have a flux getting in. So this is why we say that when we calculate the mass flow rate through the control surface, we should not consider the absolute value of velocity of the fluid. We should consider the relative velocity between the fluid and the control volume. So if the water is moving at 10 meters per second, then we can say that the velocity crossing the control volume will be 10 minus 2, which represent 8, which represent the velocity of water relative to the control volume. Okay, so this is all we should take into consideration when the control volume is moving. So when the control volume is moving, then all fluxes, to compute fluxes through the control surface, I should not use the absolute velocity of the flow, but the relative velocity of the flow with respect to the control volume. Okay, I will stress this idea more next time, and we'll do examples on it. Okay, any question on this? So if you want, just if you look at your Reynolds transport theorem now, the only variation when you have a moving control volume is that instead of considering in the fluxes term the absolute velocity v, you will just consider the relative velocity w, which is v absolute minus velocity of the control volume. Okay, Any question on this? Okay. So this is the end of this chapter. We'll see that this chapter will be an introduction for next chapter, because the Reynolds transport theorem can be applied for different variables. So as I told you today, we applied it for b equal 1. We got the conservation law for mass. Okay. Next time we'll apply it on for case of b equal to the velocity. When you apply it for b equal to v, you will get what is similar to the Newton second law in dynamics. So you'll obtain the conservation law for linear momentum. And if you put if b is the property of energy, okay, then you will end up with the first law of thermodynamics. Okay, so we'll apply the Reynolds transport theorem on for all of these cases next. Any question before we stop today? Okay, thank you. See you next time. Bye.